streamed. And the first thing we're going to do is to go over the homework assignment due on Monday, no, Tuesday. So we'll go ahead and do that. Okay, I think that's about the correct extent of the screen. Yep. Okay. On the background, we pick a pattern that has a pretty soft, end at this angle here, at this corner. So that's how I can tell where 1080 by 720 is. But some of my other classes, but to define. Pro, is known by multiple names. The main because that 1 or 2 weeks it is to have revision control because you might be able to get certain things done by a certain date. Okay, let's say the first 2 days something done, and then on the third day you did something and broke work, do not work anymore. If you do revision control, then you have to restart the version, but then you have to kind of make the comparisons. But my source code. In other words, I'm going to try this approach and go back. That didn't seem like a very good idea. Then you can go back to by another branch. So now you have two different branches from the same node, and whichever branch seems to work out better, you can just turn in that branch. Okay, after this stuff anymore. Well, it's quite knowing how to use revision control correctly is a big resume. Is what separates green graduates from graduates. If you can claim to interview I have with coding projects together, that you know, so it's, okay, so it's public for free and then private costs money. Okay, I introduced this in my cisp310 class because they have a pretty long trajectory from that class and on. And in my cisp310 class, they don't even have to write code, so revision control is not that big of a deal to them. But to you guys, since you have been writing assembly code for this class, it works on TTP-ASM as well. Basically, any text file it can analyze and keep track of the delta or the differences between versions. So it's a good thing to look into. I'm not going to talk about it in my class because it really is not in the scope of assembly language programming, but it does apply to all programming classes. So after you move on to a 4-year university, keep an eye on revision control. Use Get whenever you have a chance, so that by the time you graduate, you can claim I have used it for X many years. Is that okay? All right. Okay. So I just thought this is something that's useful for all of my classes and not just CISP300. In that class we talk about what a debugger is and a whole bunch of other stuff. So we'll kind of go back and focus on this class, and we'll talk about the solution of the homework assignment due on Tuesday, unless all of you say, nah, we got that, we don't need to talk about it. What do you guys think? Yeah, the swap subroutine. I think the Fibonacci program is due today, at the end of the day, but swap was due on Tuesday, at the end of Tuesday. So we'll talk about that unless everybody says, now we don't have to do that. People who are currently absent, of course, do not get to vote. There's no absentee voting in this case. They cannot just email and text me and go like, no, I don't want to do that. So what do you guys think? Want to do it? Okay, all right. So what I'll do is I'm going to bring up the homework assignment because I'm going to do it the same way that you would have done it. And there we go. All right, so that's function calls, and I think question number 4 has the C code. So let me see if I remember that correctly. Yep, there we go. So, and I gave you this the main code already. So let me copy and paste the C code first. And I can put it into one of my existing. This one is for bubble sort, and then we develop. It's actually pretty good. They had a Hungarian dance for quick sort, bubble sort, merge sort, and so on. So it's entertaining. They also have binary search, and they did it with Tango. So you can learn 2 things at the same time. All right, so I'm also going to copy and paste the main program because it is kind of important for you to understand how main is written in order to implement your swap subroutine correctly. Because that should remind you of the calling conventions between the caller and the callee. All right, so now we got both of those up. Very good. All right, so what we'll do is we're going to start with main. Main doesn't really have much to do. It has got 2 local variables. On line 11 in the C code, local variable x gets a value of 3, and then y gets a value of 7, and then we are supposed to call the swap subroutine so that the value of local variable x and the value of local variable y should exchange. Okay, so that's basically the job of the main subroutine. When you look at the assembly code, line 2 is just to initialize the stack pointer to quote-unquote 256, but 256 requires more than 8 bits to represent. So when you look at the truncated 8-bit version of 256, it's the same thing as a 0. And then on line 3, we allocate for local variable y, and on line 4, we allocate for local variable x. So this was done before actually when variable declared actually has a higher address, CC. Okay, but the order is as long as you kind of know, as long as you use it consistently, it would be three into A, and then we store A into D, or whatever D points to, and that initializes X because X is the able to allocate. That, that point, and that's why it worked. Copy. I don't understand why the C code is not showing. Okay, let me just do this. Let me have it auto set up again. There you go. The project get edge. You, uh, the label corresponding to this location. Push of not needing to have chances of as it makes. So this is important because you have to understand how the caller is setting up the arguments or the parameters. When we of the argument should be of one as much as possible. We have, You mean changing this part? Hmm. Okay, so if I switch this to the new way of doing things, I don't have to comment out the label definition. And then this line, I will just comment this out so that it's still here. So we will use a dot 6 plus here. So the dot, sorry, return to. So that's how we, so is that okay? Are there any questions about that? Yep. Oh, no. Back pointer. Uh, cons- then it will still be okay. On swap subroutine. Okay, all right. So the swap subroutine has, let's see, three lines of code, really, okay, but it has, a local variable definition here. So I'm going to write the swap subroutine assuming that we have access to postfix notations as expressions, just because it is now available. So the first thing we do in the swap subroutine is to decrement D, because we need to allocate for the local variable T. Is that okay? So parameters are allocated in address by and initialize own local variables. Is to allocate for my local variable T. And then after that, I'm going to use some symbolic name. And, if you worry about namespace kind of thing, you can always just kind of prefix your variable names with the subroutine. So I'm just going to call this, swap T is 0. That means, T as a local variable in swap is 0 byte away from where the stack pointer points to. It's just, a convention. And then we can say, swap underscore return address is swap T 1 plus, which means, the return address is 1 byte after my local variable T on the stack. And then we have the two parameters. So we have swap, let's see, the parameters are called pointer 1. This is the first parameter. That is swap return address 1 plus. And then we have pointer 2, which is right after that. In the final exam, if you do not want to use definitions like these, you have symbolic names instead of having to, oh, this thing is 2 bytes away and that thing is 1 byte away. But whether you want to use these label definitions or not is entirely up to you. Okay. All right. So at this point, we want to compute the right-hand side and then store that to the left-hand side. So every time you look at an assignment statement, okay, it always ends up with something like this. Okay, it always ends up with st something. Okay, we use a register here and then specify another register here. That is always the only thing. Practical purposes, we're only dealing with 8 addresses, integers, and the fair. The address of the variable in the other, this instruction, right hand side into one register. So okay, so it's kind of, we need to get what we need to put into specific registers. And if you really want things to be really super mechanical, you can always just say, I'm always going to put the right hand side into register B, and I'm always going to put the address of the left hand side into register C. Doesn't have to be, okay? But if you really want things to be kind of mechanical so you don't have to think about variations and stuff like that, you can always make that assumption. Okay. So if that is the assumption, that means B eventually needs to be the right hand side. So we'll go ahead. I think someone is blowing leaves outside. So in order to get there, okay, there's also a template of code to do this. So you use LDI, okay, whatever register you want to specify here. You can even use register C because register C can be specified later on. So you can say LDI C with swap underscore pointer one, and then you always follow this one with add CD because this will address your parameter. It's not equal address of the parameter, which is not what we want. Okay, what we want is something a little bit more complex. So the next thing we do is to dereference it. Okay, we can use a different register now. Okay, so now B is pointer 1 before register C is the address of pointer 1. And then you look at this and go like, that doesn't look like the right hand side of line 4 because on line 4 we want to dereference pointer 1. We don't want pointer 1, we want what pointer 1 is pointing to. So you need another dereference to do that. So now B is whatever pointer 1 is pointing to, that is what we want on the right hand side. Now we want to deal with the left hand side. The left hand side is kind of the same thing. You do a LDI instruction. I would use register C this time. And what we want to access is local variable t. So at this point, C is already the address of t, which is all I need. Because in order to use the store instruction, this inside, because we're going to change inside. Is that okay? So, so from line, so if this is okay, we move on to the next line in C. So we would use exactly the same kind of procedure here. We calculate the right hand side first, put it into register B. So when you look at line 5, the right hand side is kind of the same thing. There's not a whole lot of difference except it's pointer 2 this time. So we load swap pointer 2 into C, add the stack pointer to register C. So we now have the address of pointer 2. And then we start to dereference. Okay, so now we have pointer 2 in register B, and now we have what pointer 2 is pointing to in register B. Then we start to look at the left hand side of line 5. We'll start again with pointer 1 because on the left hand side of line 5 we need to find out what pointer 1 is pointing to. So we'll do about the same thing. Okay, so this will compute C is now the address of pointer 1. Then we dereference it. C is now pointer 1 itself. And we can stop using LD instructions because ultimately what we want to do is not to. So the ST instruction is here because we have the address of the left hand side in one register. We have the value of the right hand side in another register. So the store instruction will finish the job. If do, okay, off by one. Okay, I put the registers more carefully and not having to reload, re-add things, and how do I access that thing? That thing code. That makes it easier for you to kind of keep track of where am I in the evaluation. So it's a very mechanical way of translating C code into assembly code, which ends up with suboptimal and longer pieces of code. But at the same time, it is easier for a person to go through that process. So we are down to the last line in swap, which is first we have to calculate what is in T. So kind of the same thing. So we load C with swap T, and then we have an add instruction, add CD. So now, at the end of line 57, C has the address of T, which is not what I want because I know I want the value of local variable T. So a single load instruction will do that. Okay. So now register B has the value of local variable T, which is what the right hand side is specifying. And then we go to the left hand side. We start off with pointer 1, or pointer 2, excuse me. And then we add CD. So the C is now the address of pointer 2. Then we have all the dereferencing. Okay, one single dereference is all we need here. So that now C is pointer to itself. And we can stop using LD instructions now, because once we have pointer to in register C, then I can use the ST instruction to store to the location pointer to by pointer to. So that ends that would be the last instruction for that line. Do we have anything? Good. And again, it's more good. Are we good so far? Um, and this concludes the entire thing. So the exit of a subroutine is always the same as well. Okay. Um, First of all, you want to deallocate the space that you have used up for any local variables. And you can use an increment instruction if it's easy, or you can use an add instruction if it's like a whole bunch of bytes at the same time. So in this case, because t is my only local variable, increment d would be the easiest way to do it. It beats LDI. On the other hand, if you have 26 bytes to deallocate from the stack, 26 consecutive increment d may not be effective compared to loading 26 into a register and then adding that register to the stack pointer. So you kind of have to make a call of when to switch over from increments to a regular add instruction. Okay, so after this, we have the typical exit code from a subroutine, because at this point, the stack pointer is once again pointing to the return address. So that means a single load instruction is going to retrieve the stack pointer, retrieve the return address into register B, and then we can now increment the stack pointer because the return address is not useful on the stack anymore. And then we can use a jump instruction to go to the location that was stored earlier. Because every sub has a return value. So this is safe for any subroutine, whether it's value or not. The thing we need to do is to run it. You have, an idea of how to run your code to help debug it. How many people are completely done with the Fibonacci program? No one. Okay. Or no one is brave enough to raise his or her hand because it's like I don't want anyone in the class know that I'm done with it for various reasons. I used to be one of those people, so I understand. I would get an assignment in, especially in my assembly programming class. They usually give us pretty difficult programming assignments and give us like about 2 weeks of time to work on those assignments. I think one of those was a depth first in a maze. So you have to first understand how the walls of a maze is represented in a text file, and then you load it up into memory, and then you have to use depth first search to search the entire map for something. So it was like I got 2 weeks to work on that one, and I got it done in about 2 days. So when the professor said, oh, has anyone started on the homework assignment? I did not make a squeak about it. The nice thing about that is we only got 4 wired terminals to the PAX. The back any, you know, to 4 hard. This class technically has about 60 students, but only 4 was in the lab. But when you go like second to the last people, policy of no one can for more than like 30 minutes at a time. So it's kind of like a thing. So after 30 minutes, kicked out, and then you get to the end of the line, and you queue up again, and then you just do that whole thing. So basically, people stay in the computer lab like the entire night. So if you think about it that way, it's not too bad in this class as far as infrastructure is concerned. No, the next person will time you. The next person is going to be very diligent, to time you and go like, hey, that's 30 minutes, tech. But they will never see me. The TA used to use my programs, as the key to grade the rest of the class. And there was one time I made one mistake in the program, minor one, but it was still a mistake. So one particular tricky test case did not work correctly, and the TA didn't know. All right, so delete the whole thing, and then we paste the new code. Let it work out all the symbolic references. Did you guys notice the new assembler being significantly slower than the other one, or about the same? About the same? Okay, that's good to know. Okay, so this is swap.csv. I worked on this yesterday too, but this is different. Okay, maybe different, but I didn't use the same code as yesterday. Oops. Exclamation point. There we go. All right. Okay, we'll load the program in. So if I feel confident, I can just Control K, but I don't want to do that because I want to show you how you can debug your Fibonacci program. Okay, so I'm going to set up logging, and I will show you what to look in the log to help debug your program. I know this is not Fibonacci program, but they do share some elements because they use the stack, they have parameters, we have return addresses, and so on. So they do share a fair bit of traits. So the first thing I always log is the program counter, because this way, every time I move on to a new instruction, it will trigger a new log in the log file. So the program counter is always logged. And then when you look at the register bank, register D is always going to be logged as well because that's our stack pointer. We want to understand how the stack pointer is increasing or decreasing, so that always has to be logged if you want to track your program. I would track down register A, B, and C as well, because those, even though they're kind of quote unquote scratch registers, they're still important. If you really want to find out what is going on with your program, why it's not working, and so on, it's really helpful to track down all registers and not just the stack pointer. Takes up 3 additional columns, which is not a big deal. Okay. And then we want to take a look at the stack. So when you look at the stack, you're basically looking at RAM and the last few locations of RAM. So this is where you have to be, you have to kind of understand what your program is supposed to do and how many bytes it's supposed to use up on the stack. So in this particular case, main so some another byte, and then we set up arguments to call swap. Okay, parameter 2 takes up 1 byte, parameter 1 takes up another byte. Then we have the return address. Once we get local, 6 bytes will be used on the stack. I might have miscalculated something, okay? So I'm going to log 7 bytes just in case I missed something. You should do about the same kind of analysis. If you test Fibonacci with 0 as an argument, it should not do recursion. If it doesn't do recursion, then you have 1 byte for the argument, 1 byte for the return address, and we do not need any local variables in Fibonacci. So 2 bytes would be all you need for the function call itself. Now whether main has a local variable to store into and stuff like that, that's up to you to decide. Is that okay? On the other hand, if you use Fibonacci of 2, then it's going to do recursion. Okay. Now, in the recursive case, it is going to use up 1 additional byte to store the return value of the first call of Fibonacci. So don't forget that byte because you need that location on the stack as well. So in the recursive version of like f of 2, you will need 1 byte for the argument to the first invocation, 1 byte for the return of Fibonacci. For bytes, if you're gonna cost you anything, it's just gonna make the trace table a little bit more difficult to understand, but you can still always do that. And then you have to kind of decide the order. Do you want to log like location 255 first? In which order? It depends on the person. I just go from 255 and backwards, but you can always go forward if you want to. So in this case, we figured that 6 bytes should be used, but I'm going to log 7 just to be sure. Okay, double click the not register. There we go. And then we want to change this. There's no shortcut key to do it, which is kind of makes it kind of tedious. And then when you log, even though if you log to a file, you probably have to restart Logisim, because there's a bug in Logisim where, after you do one session of logging, something internally is broken. It is still a better way to do that compared to logging in a table that's internal. So we'll log everything. Huh? Oh, forgot to change one of them. Oh, it's 10. Okay. I didn't flip my glasses down, so I couldn't tell the 16 versus the 10. Oh, yeah. So they're only 6, huh? They're only 6 right now. Okay, we'll log in the extra one right there. So this is the nice thing about, counting backwards, because if you're counting back, this makes it easier to add additional stuff. All right, so I think the radixes are correct. Go to File, and we want to select temp slash swap.tsv. It's a tab separated file. Okay, and close window. So now we can just run the program at full speed and stop. So this time I'm not even going to bother to look at the RAM component nor the registers. I'm going to use the log file itself to confirm whether the program worked or not. Yep. Mm-hmm. So now so the log file itself, can be, you can open it with any type of spreadsheet program. It doesn't have to be Google Spreadsheet. So if you have Microsoft Excel or LibreOffice installed, I think that using a local spreadsheet is a lot faster compared to using Google Spreadsheet. So you can just do it that way. So temp swap.tsv. And the trick, if this is what you're using, is to label or change the column type of every single column. Instead of using standard, change them all to text. So this avoids the conversion into numbers, which makes it a lot easier to read. If it converts to numbers, it won't do it to hexadecimal numbers, and as a result, then the alignment is off, and it just makes it difficult to read. That's all. All right. So here's our trace. Okay. And just to make things a little bit easier to read, we are going to change the labeling. I must have accidentally moved register A versus register B. Okay, so we'll cut and then make a new column. Let's see. Okay, right click, insert left, and then paste here, and then get rid of this one. There we go. So we'll abbreviate this one as our stack pointer: register A, register B, register C, content at location 255, 254, 253, 252, 251, 250, and then 249. There we go. And then make all the columns a little bit narrower, because that makes it easier to look at everything on the same screen. Okay. All right. So now that we have this done, you scroll all the way to the end, and you just go like, okay, is that what I'm expecting? So you scroll all the way to the end, and this is what we see. Now, this is why X was. So as far as the conclusion of the program is concerned, it worked. But you can always double. The best thing about tracing it is you don't have to remember, because you can basically see how column F and column G used to be 7 and 3, and by the time the program ended, it became 3 and 7. So you already know, how that worked. But on top of that, you can also see when they got changed. So you just kind of scroll through the columns and you go like, oh, okay, I can see some changes right here. This row was the first change to the content of those two variables from Y to X. So the last store instruction corresponding to whatever pointer one points to gets whatever. Okay. So if a program doesn't work, then you track it from the beginning. I know it is very tedious, but that's basically what you need to do to debug your program. So in this case, the call to the subroutine swap, you can check the addresses in the assembler. So if you switch back to the assembler and go to the assemble tab gives you the most information about your program and how it was assembled. So if you're concerned about, oh, what does the stack look like when I get into the swap subroutine at the entry point, then you look up the swap label. The swap or 1C, okay, 1C is in your trace, and say, okay, that is the condition of the stack when we got into the swap subroutine. So now you switch back to the trace, and then you look at, what was it again? 1B or 1C, okay? So you can see right here, it this is the call, and so we the of invocation of Fibonacci to be recursion, right? But you can many ways that the program may not be working. One really nasty way for a program not to work is it's not returning to the right place. Okay, so what do? If you suspect your program is not returning to the right place, is you go to the assembly code and then you find out where the sequence of instructions is, when it's supposed to return. So in this case, when we are talking about swap, the sequence of code to return is over here. And then you look at column W, which is the hexadecimal version of the address. So it is at location 39. So you go back to the trace, and then you try to figure out, okay, I'm going to do one thing before we look at that. I'm just going to split the screen so that I can look at the header of the columns. Okay, not that, this one. So we can look at the header of the columns, regardless of how it scroll. So it just makes it easier to read. So you look at 39, I think it was 39, right? So you look at location 39, which is the start of the sequence of instructions to return. To the second time it's logged is because 39 changed something, okay, something else. It changed the stack pointer. So in this case, because we also log register B, you can see how register B is getting 1/6 in as a part of the sequence of instructions. How is it getting that 1/6? It's getting the 1/6 because we retrieved we retrieved from memory whatever is at location FB. We put that into register B. That's why register B got 1/6 in hexadecimal. So that is our return address. Now, if you're tracking down and you say, oh, okay, whatever we put into register B before we do the JMPB doesn't seem to match address, then you have a where my program is doing everything correctly up to this point. So I'm going to put a break. And then a single step to capture a, and you have gone to another instruction. You can't go back in time. You can go forward. Do you want to kind of mention things about your Fibonacci program? Does anyone else have any specific symptom of your Fibonacci program? Concepts used in the swap subroutine that I just did. No questions? Okay. Do we want to look at Tower of Hanoi then? We'll do Tower of Hanoi in assembly. Yeah. I mean, we can't really output anything, so it's not going to be really spectacular like in some implementations where you can actually see the disks moving from one pole to another pole. But we can implement it. Okay, so we'll take a look at that because it is recursive. Okay, and there are 2 points of recursion too. So we'll take a look at that. How many people remember what to do with Tower of Hanoi? Or how many parameters we have? Yeah, that's from 4:40, right? That's from yesterday at 4 p.m. Okay, so we can do that. Okay, the first argument is how many disks we are dealing with. Okay, so that's n. The second one is what is my from pole, what is my to pole, and what is my via pole. So from, to, and via can only be 0, 1, or 2 to identify one of the 3 poles where the disks can be attached to. Okay, so how many people are not familiar with the problem of Tower of Hanoi? Okay, so let me explain that first. Okay. Which other class talks about the Tower of Hanoi? I cannot 4:30, but it's not even data structure. I mean, this is more like algorithm than data structure. Okay, it's just kind of odd that it is classified as a data structure topic. All right, so we'll use Zerno because it really helps to look at the picture in this case. So the problem is like, okay, you got 3 poles. Okay, so this is 1 pole, this is 1 pole, and this is 1 pole. Okay, and we'll number the poles as 0, 1, or 2. Okay, so the question is, if I put some disks, okay, let's say we have 1, 2, 3, 4 disks in pole 0, how do I move all 4 disks from pole 0 to pole 2? But there are rules that we have to one at a time, plate at a time, so you can only move 1 at a time. Those are the put largest pole would not. If you see disk is anymore. So now to code it, you basically, you have, for every type of recursive subroutine, you have a conditional statement for the base case. So in this case, if n is 1, then you have an easy thing to do, okay? I can't really do anything because I don't have any way to output anything, but if you do have a way to output something, then you just basically print move disk from the from pole to the to pole, and you're done, okay? But I don't have any way to represent it in assembly code. So the else case is when we have recursion, and of course, all of these really should be unsigned integers, because you cannot have a negative number for any one of these parameters. So they should be all unsigned. So when n is not 1, okay, I'm not even checking for the erroneous case of 0, that you don't have any disks, okay, because that doesn't really make any sense. So now in the recursive version, then you call Tower of Hanoi again, and this time you are moving n minus 1 disks from whatever pole that you're moving from to the via pole using the to pole. Then you have only one disk to move, okay? And if you want to use Hanoi again, that's fine, okay, even though it's a kind of a waste of a subroutine call, but you can do that. So you can move the last disk left over from the from pole to the to pole using the via pole, which is going to be ignored in this case because you only got one disk. And then you use recursion again to move n minus 1 disks from the via pole through the to the to pole via the from pole. So that's basically how Tower of Hanoi, is one in assembly. Yeah, it's actually no. So yes, so if we can do Fibonacci, this one is actually easy. There's no need to add return value of something whatsoever, except for, oh, we need to pass n minus 1, in these particular fun because you can't. So you can look at the trace on the stack, know what disk we're moving. Not really a whole lot of. Here's in assembly using the toy processor. The time complexity of tau Hanoi, 2 to the power of the number of disks. So if it takes X amount of time for one disk, it's going to take twice of that time to solve, 2 disks. It's going to take 800% of that time to solve a case with 3 disks. It's going to take 16 times amount of time to solve like only 4 disks, and so on. If you read the original story of Tower of Hanoi, I think the monk was asked to move 64 disks, if I remember correctly. So we are talking about 2 to the power of 64 number of moves of disks, which is a pretty big, insane number. Yep. Uh, is that minus one? It is a minus one because when you have only one disk, you move it once, which is 2 to the power of 1 minus 1. Yep. But in a big old notation, it is just to the power of. The big O is only the upper bound, not theta. So in this case, we should say theta. minutes left in the lecture time. Are there any use of parameters? How to be so this class did not have an exam too, so that means the material. So the scope of the final exam, unfortunately, has to start from the end of the exam one. So anything that we talk about after exam one is going to be in the scope of the final exam. And my other class is complaining and say it's not fair. They have no idea what they're talking about. Uh, You can imagine that the heavy income sort of stuff compared to between exam two or when it should happen and exam one. So there'll be a much heavier emphasis of subroutine related stuff. So are we okay so far? I'll give you a practice test next Tuesday. So that will give you a better idea of what type of material you need to get ready for. So it would be a good idea to study over the weekend because this class doesn't meet until Tuesday. So you have to study anyway. So you might as well study now and see if you have any questions that you want to ask on Tuesday. And then after the practice exam, we have next Thursday as our last lecture. So use that class to ask additional questions that you might have of the material that we might have on the final exam. Okay. Um, One more thing. When is our final exam? Okay, that's an important thing. Okay, we'll double check. I know I have it in the calendar already or in the syllabus, but we'll double check. Um, this is spring. I don't understand why they put spring here. So I'm gonna change the URL and see whether that will work. Yep, that's what hackers do. You look at the URL and it's go like, maybe that will work, and they did. So this is a class that meets on Tuesdays and Thursdays, and the lecture time is 9 o'clock. So we are talking about this row here. So our final exam is going to be on the Tuesday um, of 18th of December, and the start time is 8 o'clock. So keep that in mind, because if you show up at night, find a place to park, that sort of stuff. The you start studying means you the to the exam. You're in class. You can bring all the program. Okay, bring those like FM. Make a link with this. I suppose computer lab, if you're working on a Fibonacci program, it's not working and you don't know why it's not working, now would be a good chance to show me and so I can give you some pointers.
So the finals were 53%?
Yep.
And then the exam was 27?
Yep.
Okay, cool.